All right. So this is lecture 11, and today is the 29th, January 2021. All right. So where are we? We have been discovering 3D equilibrium. And I sent you a handout. You have received it. I sent it by email, which has 4 or 5 problems with detailed step-by-step solutions. So I really highly encourage you to go over those. They will really help you understand the concept, especially you've seen that in 1 hour, it's difficult to do a very comprehensive 3D equilibrium problem. But nevertheless, I'm going to do one so that I can cover all the details step by step, although I have done a good job in, laying out all the steps in those handouts. But let me now demonstrate that also through another example that I'm going to do here. So the problem that I'm choosing to do, I've selected here, is in fact is one of the problems that I have in the handout, but I tell you why I'm going to redo that in here, and you will see the reason. So this is the problem. There is a rod. We have a rod or some kind of a bar that is laying against this wall. This is, if this is X, Y, Z coordinates. At this end, it is supported by a 3D pin or ball and socket joint. At this end is just laying against this frictionless wall. So obviously it can move this way or it can slide this way. So to prevent that motion, we have connected a cable from the center of gravity or the middle of this bar to connect to another point here, point C, okay? And the coordinates of all these, of course, points are given. It is in the handout, but I will just redo that here. This is 0.6 meters. Point B is, and C, they're both at the height of 0.4 meters. And the distance from y-axis for both of them is 0.15 meter. And G is in the middle, okay? So first of all, let's set up all the coordinates of all these points. We need that. So B would be 0.4 and 0.5. C is 0.4 and negative 0.15. A would be just 0.600. G is in the center, in the middle of, halfway between these two. So its coordinates would be sum of these corresponding coordinates divided by 2. That is, its X would be 0.6 plus 0 divided by 2. So it would be 0.3. Y would be 0.4 plus 0 divided by 2. So it would be 0.2. Z would be 0.15 plus 0 divided by 2. So it would be 0.075. So all the coordinates of these points are given. The problem also states that this bar has a weight. Its mass is given as 10 kilograms. So this should be multiplied by G. So that's 98 Newton. That's the weight of this bar, which obviously acts parallel to the y-axis. So the problem states this. We want to find, okay, unknown support reaction forces. What does that mean? That is those supports or devices that are holding this rod in place. This rod is connected here. So in other words, as the first step, once you set up X, Y, Z, which in 3D is all set up for you, you want to set up the free body diagram to identify those external reaction forces that you have. This weight is an applied load, is known, given. Suppose that you have, or devices that are, or mechanisms that are holding this place is, first of all, this ball and socket joint or this 3D hinge. So you have three unknowns here because rotation is allowed, right? So you have an AX, you have a force in Z direction, and you have a force in Y direction. This cable represents obviously a force. So let me call that T of GC. And then how many unknowns do you think you have at this point B? This can rotate at any direction. It's like basically what you have is something like this. So it can rotate in any direction. It can slide in any direction, right? So this is that bar, right? It can move this way. It can move that way. It can rotate in any direction. The only direction it cannot move is pushing against this plane. So that means perpendicular to YZ plane. So if I look at it like this, okay, you do have one force there, which I call that F of B, and this F of B will be parallel to x-axis. So how many unknowns you have? 1, 2, 3, 4, 5. Any questions?
How did you figure out the force of B like existing? Because like I wouldn't think to put that there.
See, think of a ladder that is laying against the wall, right? So you can rotate the ladder at the point of contact in any direction you want. You can also slide it along the wall at that point in any direction you want. In what direction you cannot move it? You cannot push it against the wall, right? It doesn't go through the wall. So wall is exerting a force to that ladder at that point, which remember that force of reaction support is always perpendicular to the direction of motion. See, this can move along this plane. So that these are the directions of motion. So if there is a force that resisting the motion against this wall should be perpendicular to this plane, and that's what FB is. Does that answer your question?
Yes, thank you.
So with those set, what is the next step? Said in 3D, you always start with summation of moments 0. You either consider summation of moment about a point or about an axis. Axis is better because you can most of the time identify an axis that intersects with most of the unknowns, so you may end up with only one equation, one unknown, which is the case here. If you consider axis AC, take summation of the moments of all forces about that, these three and this force GC, they intersect with that axis. The only forces they don't is this weight and this one. And this is known, so you end up with one equation, one unknown. This is the solution I have shown in the handout. So as an alternative, I want to show you that even if you don't detect that axis, but you can detect a point where several unknowns intersect and take moment about that point, that's also all right. So for that reason, I'm going to take summation of moments about A is equal to 0. Why? Because I have 3 unknowns here, so I end up with only 2 unknowns. What do I need to do? First of all, I have 3 forces that generate moment about point A. So I need to set up the vector equation for all these forces. And what are those? FB is acting parallel to the x-axis, so would be its magnitude times I, right? F of what I call W or G, whatever, is given, is acting in the negative direction of J, so it's just simply 98, negative 98J. How about the force in GC, or I call that TGC, right? That would be what? Would be the unknown magnitude times the unit vector of GC. And what would that be? Would be 0 minus 3, this minus this minus this divided by the length, right? So what would that be? I have done that here, so let me write it down for you. So you have T of GC times 0 minus 0.3, negative 0.3 I. 0.4 minus, I'm sorry, yeah, that's right. 0.4 minus 0.2, so 0.2 J, and then negative 0.15 minus negative, that would be negative, so it would be 0.15, okay, plus 0.075. So that would be 0.225K divided by the square root of 0.3 squared plus 0.2 squared plus 0.225 squared. If you figured that out, let me do that actually. Okay. Here, you get, okay, let me do that calculation, 0.3, okay. Okay, I have not, okay, and 0.225. Okay, that'll give you 0.425. Okay, so let me, just from clean slate, rewrite these equations because I need them. So force of B would be the unknown magnitude times I.
Hey, Professor, how'd you get 0.225K?
Because it's negative 0.15, negative this, so that would be actually negative, right? So negative 0.15 minus this. You're talking about unit vector here. So tip minus tail. Negative 0.15, negative 0.075. So that is 0.15 plus 0.075. That is 0.225.
Okay, thank you.
All right, sure. So f of W would be negative 98. J and TGC would be, I would multiply both by 10, the numerator and the denominator, makes my life easier. So I have TGC times 3 negative 3I plus 2J plus 2.25K divided by 4.25. So these are the three forces, okay? Now, I need to find the moment of all these forces about A, add them up, equate that to 0. That's the summation of moment about A means. So I need to find moment of f of B about A plus moment of FW about A plus the moment of that GC force about A and equate that to 0, right? So let's begin. We need to evaluate each of these. So that means, let's look at this. I want to take a moment of that force about point A. So I need to consider a position vector that connects that to any point along FB, which obviously would be B. So this one would be what? Would be AB cross FB. This one for W would be this position vector, which is AG cross that FW, okay? And for GC would be also this same position vector. You can consider either this or this, okay? Whichever is easier.
Professor, we can't see what you're
Oh, sorry
looking at.
about that. For this one, for this position vector, you need to connect point A to anywhere along this, right? So I would consider AG. You can consider also AC as the position vector. Okay, the reason for that is I've already got AG for the other force, so I'm going to use the same. So this would be AG cross force of GC. So let's set these up. Okay, let's do that. All right, let's do step by step. So I will start with the moment of the force AB about A. What would that be? Is AB, so I'm going to set up this determinant. F of B is unknown. I have I, J, K. FB has only X component. So you have I, 0, 0. How about this here? I have A, B. What is A, B? This position vector is 0 minus 0.6. So negative 0.6. 0.4 minus 0. So 0.4. Then 0.15 minus 0. So 0.15. So that is the moment of that force about A. So let's expand this. For I would be 0. Okay. For J, I had worked that out here already, so I'm not going to redo that. So it would be, this comes out to be, for J, would be negative 0.15. This is negative, so it becomes 0.15J. For K, which is 0 minus 0.4. So negative 0.4 K. So this is the moment of f of B about A. So this is one of them. Any questions so far? No? So let's continue. All right. So moment of the next one I had was moment of the force W, okay, about A. That is a G cross that 98 Newton J negative, right? So this would be I J K. So what is A G? That's that vector. 0.3 minus 0.6, right? So it would be negative 0.3. So I'm doing A G as a vector. 0.2 minus 0. So 0.2. And then 0.075 minus 0. So 0.075. And the force itself is negative 98 in J direction 0. So if you expand this, you have 0 minus 98 times, I'm going to redo that to make sure that we have everything correct. Okay, so I have for I have 98, okay, times 0.075. So that's 7. So it would be 7.35 I, and that would be positive. For J, I have 0 minus 0, right? For K, I have 0.3 times 98, 0.3 times 98, that is 29.4, and that would be positive. So that is 29.4 K. So this is the moment of that weight about A. So this is the second moment equation, right? One more. I need to find now moment of the TGC about A. Fortunately, the position vector is the same, is that AG cross TGC. Okay, so I've set that up. IJK. Position vector is the same, I said, negative 0.3, 0.2, 0.075. And the force is unknown, TGC. We had the force. We had worked that out. This is that force GC. So this is over 4.25. Okay. And I have negative 3 to 2.25. So let's expand that to find this moment. That will become, again, okay, 0.2 times, okay, 0.2 times 2.25, okay, for, okay, let me, minus 2 times 0.075, okay. So that becomes 0.3, it looks like it, okay. That comes out to be, this would be actually 0.3 I, okay, divide, of course, everything times TGC divided by 4.25, Okay, so this is, let me double check. 0.4, yeah, okay. So for J, 0.3, negative 0.3 times 2.25, okay, negative, okay, so would be negative, would be positive times this, so 3 times 0.075, okay, so this is 0.45, so we get plus 0.45 J, okay? And for K, you have 0.6 minus 0.6, so that's 0. So that's the moment of TGC about point A. Any questions? So you have these 3 moment equations, right? And I said, some of those has to be 0. So let me write those down, okay? And I will write them down here, rewrite them. So I need to write, okay, some of these equal to 0. So I have the first equation is FB times 0.15J minus 0.4K. That is the first moment, plus the second one is 7.35I plus 29.4K. This is the second moment equation. Then I have TGC divided by 4.25 times 0.3I plus 0.45J. This is the third moment equation. Some of these 3 vectors have to be 0. When you have a vector, right, AI plus BJ plus CK equal to 0, what does it mean? That means this has to be 0, this has to be 0. Every component has to be 0. That means you add up, if you add up these 3 vectors, right, you need to add their components. So some of i's should be 0, some of j components should be 0, some of k components have to be 0. So let's look at here. This doesn't have I. Here we have I. So you have 7.35. Here I have I. So plus TGC divided by 4.25 times 0.3. This has to be 0. Okay. How about J? Here I have J, I have FB times 0.15. Here I don't have J. Here I don't have, here I have a J. So I have plus TGC divided by 4.25 times 0.45 is equal to 0. Okay. And K, I have negative FB times 0.4, okay, plus 29.4, and there's no K here, is equal to 0. So I have 3 equations, 3 unknowns, but they're not as bad because from here, you can quickly get F sub B, which comes out to be 29.4, okay, 29.4 divided by 0.4. FB comes out to be 73.5 Newton. From here, you find TGC, okay, that would be 7.35 times 4.25 divided by 0.3, okay. Okay, now let me do that again. 7.35 times 4.25 divided by 0.3 comes out to be 104.125, but comes out to be negative, right? That means the assumed direction for that GC is wrong, but that's okay. I just leave it as that. So now you have one extra equation. What this extra equation means is what? You have already found the values. So you can just use this equation to verify if this equation is actually zero. That means the answers are correct. So if you multiply 0.15 times 73.5 plus 0.45 divided by 4.25 minus 104.125. If you add these up, okay, you will see that this comes out to be zero. That confirms solution. So anyway, by using summation of moments about a point equal to zero, we found two of these unknowns, FB and TGC. Now, how many more unknowns do I have left? If you look at the problem, these three. Now I'm going to use summation of forces equal to zero. So what does that mean? How many the forces I have are AX, right, okay, which is component of the force here, component of FB along X. FB was itself along X. So in other words, if you remember, FB was FBI. So FB is a component. So plus 73.5. And what else? Component, this one doesn't have an X component. GC has. We had, this was the GC. Okay. This is the force GC. What is its X component? Is negative 3 over 4.25 times TGC. So negative 3 over 4.25 times magnitude 104.125 is equal to 0. So this will give you AX. You do the same thing for summation of forces along Y is equal to 0. Now you have AY. This force has a component in the negative Y direction. So negative 98. This one has this component 2 over 4.25, right? So plus 2 over 4.25 times 104.125 is equal to 0. So that will give you AY. And now summation of forces along Z is equal to 0. So this one doesn't have a Z component. This one doesn't have a Z component. You have only Z component coming from here. So you have AZ plus the Z component of this force. So you have AZ. And what is the Z component here? 2.25 divided by 4.25. So you have 2.25, 4.25 times 104.25 is equal to 0. That'll give you a Z. So you found all the unknown forces. Any questions?
Would you subtract the Z component of TGC in that last one?
Yes, TGC is this one, right? That's the Z component. 2.25 divided by 4.25 times the magnitude, which we found the magnitude. Okay, so that's why I put that here. Does it answer your question?
Sort of, but that works.
No, no, no. If it is sort of, I want to clarify that. Do
I
not
just
take,
think on the last page, you didn't put the 2.25 as negative, as like a negative k component. So
oh, you mean here? Right? You mean
I
this is
didn't see what you
negative?
pointed at. Oh, no, on the other page, on the other side, when you transferred it to the oh
Oh, you mean this one?
yeah, that one.
Ah, you should have told me this is negative. You were right. So that carries through, right? So this is negative, right? So for J, you end up actually, this is positive minus positive, and that the value doesn't change because this is positive and this is positive. So you may end up with negative here, right? Okay. The answers should be okay because I have the answers. It only the sign with effect, which is affected. And that sign is affected right here. Okay. I'm glad you noticed it. Yes. Good point. Any other questions? So sort of became more clear. Now it is clear, right? That was my error. Any other questions? So as you see, 3D problems are not difficult. It's just that the process takes much longer, or the problem, you know, it takes a lot of time. So the question that always comes up is that, wait a minute, so how do you expect us to solve a problem like this on the exam? The answer is usually the 3D problems given on the exams are such that you don't have that many operations, or let's put it in simple form. The problem is a whole lot easier. It's not as involved. You don't have that many unknowns, or the problem is such that geometry is so straightforward that you can quickly solve, you know, those problems. So for that reason, let me show you, go over a typical exam problem. We have time, so I'm going to do that. This is an exam problem from, in fact, last quarter. So let's do that, okay? So, okay, somebody has a question. Danielle, what was the class average for the first exam? Oh, I'll tell you about that later. Okay. So let me bring this up. Okay. All right, I'm going to do this problem, which is a good problem. Okay. So this is the problem. We have a frame type structure like this, which is an F shape 3D. Okay, move it this way. 3D frame. Okay. looks like this. Okay, here we go. So this point C is sitting just on a 3D ball. In other words, almost like a 3D roller. That is the only direction. Again, like that other problem. The only direction, this can rotate in any direction. It can move this way, you can move that way. The only direction it cannot move is in this direction. At this point B, you have a kind of a hinge, but the hinge is such at point B, and by the way, these values, these dimensions, let me give them to you, 0.4 m, 0.4 m, 0.4 meter. This is 0.6 meter, and this is also 0.4 meter. So this is A, this is B, this is C, and this is point D, okay? So you have a ball and socket joint at A. That means all rotations are allowed. The only thing that is not allowed is movement in these three directions. You have an applied load of 900 Newton acting at point D. At B, you do have a special kind of a hinge that the problem explicitly states that the only two unknowns or motions that are restricted are in this direction and that direction. So in the exam, as far as the unknown goes, they're either so easy that you can detect, like this one, or you have been given explicitly what unknowns you have here. So the problem is asking you to find all support reaction forces. Okay. So let's do that. XYZ is given. As far as the free body diagram, which is the key, let's set that up. You have three unknowns here. This is AX, AY, AZ. Here, as I said, the problem says you have only two unknowns in this direction, BY and BZ. And here, obviously, you have only a vertical force at that point. So you have 1, 2, 3, 4, 5, 6 unknowns that you want to solve for. Okay? So this is what I do.
Professor?
Yes.
So I was curious with how you determine what unknowns you have. Does that depend on what kind of hitch or
You mean
there
at B?
is?
You mean at B or these?
Just in general, when you're determining the unknown forces that have to
Okay.
do with the hinge that you have?
Yes. You look at A. Let's go with A first. A is a three-dimensional hinge. A hinge means what? Rotation is allowed in all directions. So there's no moment.
Mm-hmm.
But the movement, translational movement, is prevented in those three directions. That means you have three unknowns, like X, Y, and Z, three unknown forces. So that is that clear as far as A goes?
Yes.
As far as C, you just have this sitting on a ball. Think about you put your foot on a soccer ball. You can move your foot in two directions, but you cannot push the ball into the ground, right? That
Mm-hmm.
means the ground is exerting a force, and you can also rotate in any direction. So this connection represents only one force coming from the ground. At B, since this is a special hinge, the problem explicitly says that what this represents is a device that only prevents translational motion in Z and Y direction, and rotation is allowed in all directions, and motion is allowed along X direction. So this information you're explicitly given. You don't have to guess.
So are the unknowns where the movement is restricted?
Exactly. Because when you have restriction, that means you're resisting a force, right? Or a moment. That's what the meaning of unknown support forces are. Whichever direction you try to push a tree in whatever direction, you cannot bend it at the base. That means at the base, you do have a moment that is resisting. Also, you cannot move the base in any direction. So that base also represents three forces in every single direction. So that's how you visualize the unknown forces. Did that answer your question?
Yes, thank you.
Sure. So, oh, by the way, I'm sorry, the axes are given like this. This is Y, this is X, and this is Z. So I should correct that. This is AY, this is AX, this is AZ, and this is CY, not CX, okay? So this is BX, and this is BZ. All right. So if I want to solve for the unknowns, you can quickly see in this problem that the summation of moments about an axis is the best. And what would be that axis? Look at the y-axis. See? These forces all intersect with that. So the only unknown you have is Cy. So I'm going to take summation of moments about y. But what about it? If I do that, you honestly don't have this is not going to be a 3D problem, becomes a 2D problem. You know why? Because you have the vertical distance from here to this line. You have the vertical distance from here to this line. So if this rotates this way, okay, this is going to rotate that way. So if you look at the problem in this, from this eyesight, you have a 2D problem. If I draw that like this is Z, this is X, what I have is I have this 900 Newton at 0.4, and I have this CY, which is at 0.6. Can you see that? Can you visualize that? So I have just 900 times 0.4, which is positive, minus 0.6 times CY, which is negative. That'll give me immediately CY. That comes out to be 600 Newton. See, the problem is very easy. This is the way these exam problems go. Now look at this. If I write summation of forces along y equal to 0, how many unknowns I have in this direction? Only AY. Any other forces? No. So AY would be 0. Okay. Now, if I take summation of moments about X equal to 0, or about point A, doesn't matter. Summation of moments about point A is equal to 0. Okay. I have this force, and this force. But if you use a little bit of imagination, this is not really a 3D problem because you have vertical distance from this point to all of these forces. So this force, which is BZ, about point O or about X, is rotating that way. So it's going to generate a moment of 0.8 times this, which would be about x. This does not generate a moment about x because it's parallel to it. How could it? This one generates a moment also in that direction. So you have cy, which we already found, times this distance, 1.2. And this one would be in the opposite direction. So it would be negative 900 times 0.4 equal to 0. So that will give you BZ that you can quickly find. And that would be 450 Newton. Once you find that, okay, now you go with the other ones, okay? But the time doesn't allow me. So what I'm going to do, and before I forget, in fact, let me do this. I am going to send you this problem through email right now because it's a very good problem. And before I forget, I'm going to do that.